Today I want to talk a little bit about bond strength. And bond strength has to do with a number of different factors, but I want to kind of touch on it in both ionic compounds and molecular compounds. So both ionic bonds between cations and anions, and covalent bonds where we're sharing electrons, and kind of the different things that impact how strong these bonds can be. And as you could maybe surmise, if you've studied a little chemistry, a lot of it has to do with where the two elements are on the periodic table that are involved in the bonding. So the strength of a chemical bond in general is determined by a number of factors. I have two of them here, but we're going to expand on the length part in a little more detail later. So length, the longer the bond, the weaker it is. The closer together that the atoms are, or the nuclei of the atoms are, then the stronger the bond. And again, there's a number of factors that feed into length as well, which we'll get into and unpack in a second. And then also polarity is something that that the strength is related to. So how much of an unequal sharing is there for molecular compounds or molecular bonds, covalent bonds, where we're sharing electrons, but it's either equal or unequal. The more unequal the sharing, so the larger the difference in their electronegativities, the less stable the bond is, the easier it is to break, the weaker it is, if you want to think about it that way. Now, bond strength, when we're talking about a definition, is enthalpy, and we've talked about enthalpy in other videos when we're talking about the energy of different processes. So this, in this context, is a delta H, and it's the amount of energy that it takes to break the bond. So if I have kind of two things bonded together, X and Y here, the amount of energy that it takes, the amount of enthalpy that it takes to break this bond, is the bond energy. And that strength then and the energy are intertwined. Now, kind of conversely, when you put these things together, when I form this bond between X and Y, then there's energy that is released, and that's kind of the negative amount of that bond energy or bond enthalpy. Now, I have a kind of a clarifier here at the end that it's really talking about bonds and molecules in the gas phase. And this is really more about thermodynamic quantities and the way that we measure these things, that it's just easier to measure these things in the gas phase. And so we talk about most of the bond strength, breaking bonds, and enthalpy processes for various phase changes or chemical reactions of gas phase molecules. And of course the phase matters, but the standards are in the gas phase. Okay, so let's unpack these in a little more detail. Let's talk about length a little bit more. So the bond length is really defined as the sum of the atomic or ionic radii. So the radius for whatever element A is plus the radius for B is the bond length for the AB bond that forms between them. So if I have these two atoms, we can think about them as spheres. This is a horribly drawn sphere. I apologize for my poor art skills per usual. So if I have a sphere here that represents atom A and a sphere here that represents atom B, then that radius here for A and the radius here for B, this distance is my bond length. Now this is going to be true whether it's a covalent bond, so we have a shared pair of electrons, so we have a non-metal and non-metal A and B, but it could also be true if we're talking about ionic bonds, where these are ions. So if I have ion A and ion B, then we have what is called the ionic radius instead of the atomic radius, and that still gives us information about the bond length. Now, in general, atomic radius increases going down the columns, down the groups. So if we're looking at atomic radius in terms of periodic trends, it increases going down and it increases going from right to left. So our largest atomic radii are over here. When we're thinking about ionic radii, so thinking about the ionic version, anions get larger because we're getting more electrons, right, the negatively charged ones. So our anions or nonmetals tend to get bigger than the atomic radius on its own, and cations get smaller. Recall that electrons account for the volume of an atom, right? So in the volume, if I'm losing electrons and forming a cation, then I'm going to get smaller. If I'm gaining electrons and forming an anion, then I'm going to get larger. And we see those trends that still follow this general trend within the periodic table. Now, of course, this is just an approximate because radii are approximate, because atoms and ions aren't technically spheres, right? It's just an easy way to model these things and an easier way to visualize this length. So this is kind of an approximation, and it is influenced by a number of different things. So if this is A to B with just a single bond in between them, then it's going to have that particular bond length. But that bond length can change if we have something like a double bond between A and B, for example. And again, the shorter the bond, the stronger it is. So the closer together these nuclei are, whether it's covalent or ionic, then the stronger the bond is. It would take more energy to break that apart the shorter it is. Now this relates to an idea called bond order, which is in molecular compounds, and relates to what I was talking about above with the single versus double bonds. So if I take a molecule like methane here, then it just has single bonds in it. And I would say that the bond order for this single bond is 1. Has a bond order of 1, which just means that it's single. Whereas in my carbon dioxide here, I have 2 shared pairs of electrons between my carbon and my oxygen. 2 shared pairs there. So I would say that this is second order. So that means that it's a double bond. And if I had a triple bond, then it would be third order if we're talking about our bond order. Now usually we think about these in whole numbers because we're talking about the number of pairs of electrons that were shared. So we have 1 shared pair of electrons there is bond order of 1, 2 shared pairs of electrons, bond order of 2. Now when I have something that has the potential for resonance structures, so let's take our sulfate ion here. Now, the way that I've drawn this, I have kind of alternating double and single bonds, but that's not really true. With resonance structures, and what we've seen in other videos is that this is really more of kind of a bond and a half, right? So they're sort of shared by these 2. This is sort of shared by these 2. It's not really that there's 2 double bonds and that there's 2 single bonds. It's really more that everyone has about a bond and a half. So we would say that the bond order for these guys with resonance structures here would be 1.5, right? So this is kind of a bond and a half. And we'd only really see this in resonance, where there's that delocalization of electrons. So the electrons are kind of fluidly part of the structure. They're not really associated or affiliated with the space between 2 particular atoms. So this is our resonance kind of idea. So we like to say, oh, well, they're whole numbers. 1 is single, 2 is double, 3 is triple. But we can have some squishiness here depending on how many bonds are sharing these delocalized electrons. So this idea of bond order then relates to the length, because a single bond is much longer than a double bond, right? If I have more shared pairs of electrons, then these things are tighter, more tightly bound together, right? Or a bond and a half here is going to be more tightly bound than a single bond here. So the number of shared pairs of electrons influences the length, which then in turn influences the strength. So let's talk about what we mean by strength then. So as defined early on, I said that this is the bond enthalpy. So this is the amount of energy that it takes to break the bond. That's the definition of it. So that amount of energy is related to how strong it is, and how strong it is related to the length and the polarity and atomic radius and all sorts of other features here, the bond order. Now, bond enthalpy is always going to be positive because it always takes energy to break bonds. When that bond forms, that is always going to be negative. In fact, it's going to be the negative bond enthalpy because that's the amount of energy that comes out when that bond forms. So when we're calculating this in an overall reaction, let's take this reaction here with ammonia and elemental iodine. It gives you this NH2I and this hydrogen iodide. Then if I wanted to calculate the energy of this process, I need to kind of map out what's happening. I start off by saying, well, I'm going to be breaking these bonds, right? Specifically one of them. And I'm going to be breaking this bond. And then these guys are going to join up. And these guys are going to join up, right? That's kind of what's happening going from my reactant side to my product side. So this bond breaks, one of these iodines jumps on here. And again, I kind of have it flipped just for ease of my artistic skills are already being taxed by this. And then when this guy breaks, then the other one is going to join up with that hydrogen. Okay, so if we're mapping out what's happening on kind of a what's being broken and what is forming kind of level, then this is what's happening. And the overall energy of this process is going to be equal to the bond enthalpy for the breaking of my NH bond. Kind of, here's my reactants here, plus the bond enthalpy for breaking my iodine bond. And we're going to subtract from it the amount of energy that we get out from these guys, and that's going to be the bond enthalpy of my Ni here, right, from the formation of this guy, plus the bond enthalpy of my Hi, which is the formation of this guy. So my reactants, right, the energy of the reactants here that I had to put in order to break these bonds, minus the amount of energy that I have, that I'm going to get when I am forming these guys. So when I look at tables, then I look up these bond energies for these individual bonds, and I can say that my delta H is equal to, here's 391 kilojoules per mole. Again, totally look-upable. And if I would have had more than one of these types of bonds that broke, in this case I just have one of each, so I'm just doing these one of each, but if I had more than one, then they would act as multipliers, so I would just multiply by the number of bonds that are being broken. And here's the number of kilojoules per mole for the bond enthalpy of my nitrogen to iodine. And then I'm going to add to it my 299 kilojoules per mole. This is my hydrogen iodide. So again, the sum of my reactants minus the sum of my products. This feels a little bit different because we've talked before about how the delta H for a chemical process is the sum of the energies of formation of the products minus the reactants. But in this case, we're talking bond enthalpy. So this is how much energy it takes to break these bonds minus how much energy I'm going to get to form them. So the way that this is set up is correct. And this is reactants and products. It's a little bit wonky, especially from the way that we've talked about delta H in other videos. So when I plug these in, then I end up with a positive 74 kilojoules per mole. So net-wise, this is an endothermic process. This is a positive value, so it takes more energy to break apart these bonds than I get out, right? So that's what this tells me at the end of the day here, right? I had a goodly amount of energy here that came out, but it wasn't enough to counterbalance the amount of energy it took to break the bonds in the first place. So we have more stable reactants, stronger bonds there than I've formed in my products. Now again, bond enthalpy, bond length are all related to each other. They're related to the strength, they're related to periodic trends, and then these calculations can come from very look-upable values, and you can manipulate these if you know how to draw the Lewis structures and you understand what's happening going from the reactant side to the product side. It takes energy to break bonds, you get energy when they form. If you have any questions on this, don't hesitate to reach out. Otherwise, I'll talk to you again soon.